Welcome back to the deep dive. You know, we spent a massive amount of time on this show just staring up at the skyscrapers.
Yeah, the really big stuff.
Right. We talk about the sheer scale of things like GPT-4, Gemini, Claude, these towering achievements of modern AI. But today we're doing something a little bit different. We are going down to the basement.
We are checking the foundation.
Exactly. We're looking at the bricks themselves.
Right.
Because there's a new paper out from a powerhouse team at MIT, Caltech, and Northeastern.
Including folks like Max Tegmark, by the way.
Yeah, huge names. And this paper basically suggests that we might have been building with the wrong bricks for the last decade.
It's a bold claim. I mean, in the world of deep learning, the quote-unquote brick has been the multi-layer perceptron.
The MLP.
Right, the MLP. It's been the default for a very long time. If you download a neural network library today, that is what you get.
And this new paper introduces a challenger called K.
Kolmogorov-Arnold networks.
Right, K-ANES. And the promise here isn't just that they're slightly better. They are talking about models that are potentially more accurate with a fraction of the parameters.
A tiny fraction.
And this is the part that really blew my mind. They are fully interpretable.
Which brings up the whole glass box versus black box debate. That is crucial for science.
It really is. So our mission today is to just unpack all of this. How do you rewrite the fundamental rules of neural networks using, a math theorem from the 1950s?
Yep, 1957.
Right. And does this actually mean we can stop staring at black boxes and finally start understanding what the AI is actually thinking?
Well, to understand that, I think we have to start with the status quo. You mentioned the MLP earlier. We really need to visualize what that actually looks like to grasp why CANs are such a radical departure.
Okay, lay it out for us, because when we say neural network, most of you listening probably picture that standard web diagram.
Yeah, dots connected by lines.
Dots and lines, exactly.
Yeah, precisely. You have layers of nodes, let's just call them neurons, and they're connected by edges. In the standard MLP architecture, the learning, the actual intelligence of the model, it lives on the edges.
On the lines connecting the dots.
Yes. Each line has a weight. Think of it kind of like a volume knob. Signal comes down the line, and the weight multiplies it. It just turns the volume up or down.
And it's just a linear operation, multiplication.
Exactly. Just simple multiplication.
Okay, so the lines are volume knobs. What about the dots themselves?
The dots are where the activation function lives. This is a nonlinear rule. And it's usually something fixed and really simple.
Like what?
Like, if the number is negative, make it 0.
Oh, real U.
Right, real U. That's a very common one.
So just to summarize, the standard model, the processing stations, the nodes, they're completely fixed. They don't learn anything.
They just follow a simple rule.
Right. And the connections, the lines, they are just simple multipliers that get tweaked during the training process.
That is the fundamental recipe of deep learning. Fixed activation on the nodes, learnable weights on the edges, and, I mean, it works.
That's why we have ChatGPT.
Exactly. But CANs flip this entire structure completely on its head.
When you say flip, do you mean literally?
Literally. The authors of the CAN paper essentially asked, what if we remove the linear weights entirely?
Wait, so no volume knobs on the lines?
None at all. Instead of a simple number, every single edge in a CAN becomes a learnable nonlinear function.
So the wire connecting the neurons isn't just a multiplier anymore. It's kind of like a shapeshifter.
Shapeshifter is a great way to put it. They use something called B-splines.
Okay, splines.
Yeah, if you've ever done vector design or used a tool like Adobe Illustrator, you know how you can draw a curve and then pull on those little control points to bend it?
Oh, yeah. Bezier curves. You pull the little handle and the line swoops up or down.
A spline is essentially that. In a CAN, the learning process is the network figuring out the absolute perfect shape for that curve on every single connection. It's not just turning up the volume anymore. It's completely reshaping the signal as it travels from one neuron to the next.
That sounds significantly more complex for the edge. So what happens to the nodes then?
The nodes become completely boring.
Boring.
Yeah, in a cold CAN, the node just sums up everything coming into it. That's it. No fixed rules, no read OU. The complexity moves entirely from the node to the edge.
Okay, so we've inverted the architecture. Complex edges, simple nodes. Why do this, though? Is it just to be different, or is there an actual mathematical reason?
It goes all the way back to the Kolmogorov-Arnold representation theorem from 1957.
All right.
It's a mathematical proof that basically says any complicated multivariable function can be broken down into a sum of simpler single-variable functions.
But if this theorem is almost 70 years old, why are we only building AI with it right now? Why stick with the MLP brick for so long?
because for a very long time it was considered theoretically sound, but practically useless.
Useless how?
The functions in the original theorem could be wildly jagged,
Yeah.
like fractal, non-smooth curves. You couldn't train a computer to learn them. They were an absolute nightmare for optimization.
Oh, I see. So the theory existed, but the engineering to actually do it was impossible.
Exactly. And the breakthrough in this new paper is that they generalized it. And they didn't stick to the strict two-layer structure of the original
They
theorem.
just stacked them.
Yes, they stack these CAN layers deep, just like we stack layers in a standard deep neural net. And by using those smooth B-splines we talked about, they found they could actually train these things.
And this stacking, does that help them beat the curse of dimensionality? I saw that mentioned.
The dreaded curse. Yeah, in data science, as you add more input variables, the problem gets exponentially harder.
Right.
Traditionally, splines are terrible at high dimensions. They just fail. But by stacking them, CANs can decompose a really hard, high-dimensional problem into small, manageable pieces.
It's the classic divide and conquer strategy.
It is. And that leads directly to the first major win they found, which is all about scaling laws.
We hear about scaling laws constantly on this show with LLMs. Usually, it's just add more data, add more compute, and the model gets smarter.
True, but there's a diminishing return. With MLPs, the curve is somewhat shallow. You have to throw a massive amount of parameters at the model just to get a small boost in accuracy.
And KNs defy that.
The paper claims they scale much faster. Theoretically, the error rate drops as n to the -4, or n's the number of parameters.
And for MLPs.
It's much, much slower. In their experiments, they did things like fitting a Bessel function or complex geometric shapes. The MLPs would just hit a ceiling. They'd plateau.
But the CANs didn't.
Right. The CANs kept getting more accurate. They hugged that highly efficient scaling line perfectly.
So basically, for every dollar of compute you spend, you're getting far more intelligence out of a CAN than an MLP.
In these specific function fitting tasks, yes, absolutely. And there's another feature related to this that I think is even cooler. They call it grid extension.
I read this part. It sounded a bit like upgrading your TV without actually buying a new one.
That is the perfect analogy. Think about how we train models right now. If you train a small neural network and you realize, it's just not accurate enough, what do?
You throw it away. You build a bigger architecture, and you have to start training all over from scratch.
Right, and it's incredibly wasteful. But CANs don't work that way at all, because the learning is stored in those spline curves, and splines are defined by a grid of control points.
You can just add more points.
Yes, you can just make the grid finer. It keeps the exact shape it has already learned. The knowledge isn't lost, but now it has more flexibility to fine-tune the details.
So I could start with a, say, 480p model, train it really quickly, and then just switch it to 4K resolution to finish the job.
Exactly. It allows for a real hierarchy of learning. You learn the broad strokes first, then you refine. MLPs just cannot do that.
That alone seems like a massive efficiency win. But I want to pivot to the glass box aspect of this, because to me, the biggest problem with AI right now isn't that it's not smart enough.
It's that we don't trust it.
Exactly. We don't trust it because we have no idea how it works.
This is really where CANs separate themselves from the pack. The paper describes a whole pipeline to take a trained CAN and turn it into a pure mathematical formula.
But how is that even possible? Even if the edges are these nice, smooth curves, isn't a deep network still a messy web of thousands of curves?
Ideally, yes. But CANs have a trick up their sleeve called sparsification.
Sparsification.
Right. Because those activation functions on the edges are learnable, the training process can actually drive the useless ones entirely to zero.
Oh, so it effectively cuts the wires that aren't doing anything.
It prunes the dead branches. So you start with a fully connected web, but after training, you might be left with a very sparse, clean skeleton. You can visually see exactly which variables are talking to which.
Okay, so you have this clean skeleton. But how do you get from a skeleton of curves to an actual equation, like E equals MC squared?
That is the symbolic regression step. The KAN looks at one of those surviving curves, and it checks a library of mathematical functions. It literally asks, does this curve look like a sine wave? Does it look like an exponential function? Does it look like x squared?
It's like autocorrect, but for math.
That's brilliant. Yes, it snaps the approximation to the exact symbol. And the paper walks through a really great example of this with a hypothetical user named Alice.
I loved the Alice example. It made it so concrete. So Alice is a scientist, right?
Alice is a scientist, and she has a data set. She has inputs X and Y, and she has an output. Now, she doesn't know the underlying law, But for the sake of the example, we know the data was generated by a specific formula.
What was it?
Function of x and y equals the exponential of sine of pi x plus y squared.
That's a bit of a nasty function. Signs inside exponentials.
Right. If you threw a standard deep learning model at this, it would predict the output perfectly. But it wouldn't tell you the formula at all. Alice would just have a black box predictor.
So she uses a can instead. What's step one?
Train the can. It learns the basic shape. At this point, it's messy, but it's accurate.
And step two?
Prune it. The network realizes a lot of the connections are just noise, so it zeroes them out. Suddenly, Alice sees a clear structure.
She can actually look at it.
Yes, she sees that x goes through something that looks very much like a sine wave, and y goes through something that looks like a parabola.
And this is where the human comes in.
Right. This is the true collaboration part. Alice can look at that curve and say, that looks exactly like a sine wave. She can then manually fix that node to be strictly a sine function.
She forces the math onto it.
She provides the hypothesis. Then she retrains the rest of the network to adjust to that fix. She does this iteratively. And in the end, the KN outputs the exact formula. 1.0 times the exponential of 1.0y squared plus 1.0 sine of 3.14x.
That's amazing. It didn't just approximate the data. It literally discovered the source code of the data.
And that completely distinguishes it from traditional symbolic regression, which is often very brittle.
Brittle how?
Usually, if you don't guess the structure of the equation perfectly right at the start, traditional methods just fail. Cans search continuously. They find the structure, first the skeleton, and then they find the math.
Now, Alice is a made-up person, but the paper claims they did this for real scientific problems, too. They mention knot theory.
This was the drop-the-mic moment for me. They took a data set from a recent DeepMind paper.
And DeepMind is the gold standard.
They absolutely are. DeepMind had used a standard MLP to predict a geometric property of knots called the signature. It's a highly complex problem. Their MLP had about 300,000 parameters.
Okay, 300,000. Keep that number in mind.
And it achieved about 78% test accuracy. The CAN researchers took that exact same data set. Their CAN achieved 81.6% accuracy.
Higher accuracy with how many parameters?
200.
Whoa. Wait, not 200,000, just 200.
Just 200. That is 3 orders of magnitude smaller. It's basically the difference between a supercomputer and a pocket calculator.
That is absurd. How is that even physically possible?
It's possible because the MLP was just brute forcing the problem. It was memorizing the entire landscape. The CAN, because it was so small and so constrained, was forced to actually find the logic. It had to find the underlying rule.
And because it was a glass box, they could actually see the rule?
Immediately. They looked at the graph and saw that the knot signature really only depended on 3 specific variables out of the 17 inputs. The CAN just ignored the rest entirely.
So it isolated the variables?
Yes. It essentially rediscovered the mathematical relationship DeepMind had found, but it did it completely autonomously.
So it's not just efficient, it's insightful. It tells the human scientists exactly where to look.
Exactly. And they did the exact same thing in physics with Anderson localization.
That's condensed matter physics, right?
Yes. They were looking for the mobility edge. It's the boundary where a material switches from being a conductor to an insulator. So a phase transition.
And they used the Alice method for that.
They did. The human scientist had a hunch. They said, I think this involves a cosine function. And they injected that into the CAN. The CAN did the heavy lifting for all the rest. It extracted the exact theoretical formula for the mobility edge.
Wow. This really feels like a shift from AI as an oracle, where you just ask a question and blindly get an answer, to AI as a research assistant.
A research assistant that fluently speaks the language of functions. And actually, that brings up another biological comparison the paper makes. They talk about catastrophic forgetting.
Which sounds exactly like what happens to me after a long weekend. But in AI, this is a serious flaw, isn't it?
It's a huge flaw. If you teach a standard neural network to recognize cats, it adjusts all its global weights. If you then try to teach it to recognize dogs, it adjusts all those exact same weights again.
So it overwrites the cat memories.
It does. It forgets task A to learn task B.
Because the brain of the MLP is global. Everything touches everything else.
Exactly. But remember, cancers are built on splines, and splines are fundamentally local.
Local in what sense?
Imagine a really long rope lying on the ground. If I pick up one end of the rope and wiggle it, does the other end of the rope move?
No. Only the part near your hand moves.
That is exactly how a spline works. Modifying a control point in one specific region of the data doesn't affect the curve in another region at all.
So I can teach the CAN something completely new in this corner of the data, and it won't mess up what it already learned in that corner.
Precisely. They showed this with a toy example of learning 5 Gaussian peaks.
Basically 5 bumps on a graph.
Right, 5 bumps. They tried to teach the models the bumps sequentially. The MLP completely failed. It kept smoothing over the old bumps to try and learn the new ones, but they can learn them one by one, preserving all the old ones perfectly.
That is so much closer to how our human brain actually works. We have local plasticity. I mean, I don't forget how to ride a bike just because I learned how to drive a car.
Exactly. It suggests CANs might be a much better path toward true continual learning, where an AI can grow and adapt over time without needing to be fully retrained every single time it sees new data.
Okay, I have to play devil's advocate here for a second. We have a model that is more accurate, massively more efficient with parameters, fully interpretable, and doesn't forget things. This sounds completely perfect. Why aren't we running GP085 on CANs right now? There has to be a catch.
There is a catch.
Yeah.
And it is the classic computer science trade-off. Speed.
Is it slow?
It is very slow. Now, not in terms of how many steps it takes to learn. It actually converges very fast mathematically. But the wall clock time, the actual time you sit there waiting for the computer to finish, is significant. The authors estimate it's about 10 times slower to train than an MLP currently.
10 times? I mean, that's a deal breaker for training a massive foundational model.
It is. If GPT-4 took 3 months to train, you really don't want it to take 30 months.
Why is it so slow, though? Is the math just too hard for the computer?
It's not that the math is hard, it's that our current hardware just isn't built for it. We have spent the last 20 years optimizing GPUs to do exactly one thing really, really well: matrix multiplication.
The MLP brick.
Right. MLPs are just giant stacked matrix multiplications. NVIDIA has essentially built the superhighways specifically for that type of traffic. CANs, with their individual activation functions on every single edge, are doing something fundamentally different. They just can't take advantage of that highly optimized batch processing as easily.
So it's like trying to drive a train on a paved road. The engine is super powerful, but the infrastructure is completely wrong.
That's exactly it. The authors are very optimistic, though. They see this strictly as an engineering problem, not a fundamental physics problem. They think that with custom CEDA kernels, or maybe even entirely specialized chips down the line, that speed gap can be closed.
But for now, we aren't replacing the transformer architecture.
No, definitely not. I think the immediate future isn't CANs replacing LLMs for text generation. It's CANs completely taking over the AI for science niche.
The niche where truth actually matters more than fluency.
Exactly. If you're generating a poem, you really don't care about the underlying differential equation. But if you were trying to model nuclear fusion, or predict global weather patterns, or discover new life-saving drugs, you need absolute precision. And you need to understand the why.
The paper used a phrase near the end that really stuck with me. They called them language models for science.
I love that framing so much. We usually think of language as English or Python, but the true language of the universe is functions. It's math.
And CANs are native speakers.
They really are. We're moving from a world where we prompt an AI to write a blog post to a world where we might prompt an AI to discover a natural law.
Hey, Can, here's the raw data from the particle collider. What's the formula?
Right. And instead of a hallucinated paragraph that just sounds plausible, it gives you a rigorous mathematical equation that you can actually go into the lab and test. That is a very different and potentially much more powerful future for AI.
It really makes you wonder what else is hiding in the basement of mathematics that we just completely ignored because computers weren't ready for it yet.
I think we're going to see a lot more of this. Revisiting old, dormant theories with modern compute. The Kolmogorov-Arnold theorem was definitely a sleeping giant.
Well, I, for one, am incredibly excited to see what happens when the hardware finally catches up to the math. For you listening, if you want to actually see these networks, because the visualizations of the pruning process in the paper are weirdly satisfying to watch, we have linked the full paper in the show notes.
And for the coders out there, the project is entirely open source. It's called PyCan. You can pip install it today and start training your own little glass boxes.
A new brick for a new kind of building. Thanks for walking us through it today.
Always a pleasure.
That's it for this deep dive. We'll see you next time.